Okay, students, Chem 30, Thermodynamics Lesson 6, Hess's Law using enthalpies of formation. So we're going to accomplish the same thing as we did in Lesson 5, but we're going to use a different method. We're going to calculate enthalpy change using enthalpies of formation. I just call this Hess's Law the short way instead of the long way like in Lesson 5. So in this lesson we use what we call formation reactions, or enthalpies of formation. That's the change in enthalpy when 1 mole of a compound is formed from its elements. So we look in our data books on pages 4 and 5. So get those out, take a look at that. Here's what the top of page 4 looks like. It says standard molar enthalpies of formation. Then it gives us our kilojoules per mole, or delta FH. And we could have the M there for molar. But because they've said molar and have moles there, they're not writing it in there. Anyway, take a look at ammonia. Ammonia, NH3, negative 45.9. So what does that really mean? Well, let's look at another one. Carbon dioxide, CO2, negative 393.5. Here's what that means. That means negative 393.5 kilojoules per mole are released or are exothermically given off, negative, when this happens. Because this means formation, formed from its elements. When CO2 is made from C and O2, it gives off 393.5 kilojoules. Okay, that's what molar enthalpies of formation are. Okay, and all that really means is this: when C and O2 combine and form the compound CO2, 393.5 kilojoules are given off. Okay, now here's our formula for today. Yesterday we simply manipulated equations and produced a desired equation, and then we did our calculation. Today we have this formula. Alright, this means the sum of the moles times by all these together mean the molar enthalpy of the molar heat of formation of the products. Subtract the sum of the heat of formation of the reactants. Okay, so what does this look like? Well, let's say I have to figure out the enthalpy change for the molar enthalpy of combustion for methane. Some students will look in the data book, they'll find methane, negative 74.6, plug that in. That, of course, would be wrong because the question doesn't say the enthalpy of formation for methane. It says burning or combustion. If this equation was C plus 2H2 produces CH4, yeah, we could just plug that in. But this is not a formation, this is a combustion. So we have to use this formula. So let's go through it. I start with my products. There's my products, CO2 and 2 waters. Now I've done all the work here for you, but let's back up and I'll go through it. Let's start with the first product, carbon dioxide. I have 1 mole of carbon dioxide, and then I go look up the delta FHM, the heat of formation. That's in the data book, carbon dioxide formation, negative 393.5 kilojoules per mole. I go ahead and plug that in. Now you might say, wait a minute, you can't, why are we using delta FHM's formation reactions in this combustion reaction? I will explain that near the end of this lesson. Let's just go with the calculations for now, then I'll explain the chemistry. Okay, so 1 mole of CO2, I multiply 1 by 393.5. Great. Next, I have 2 waters. 2 moles, there's my 2, times by water. Now be careful, there's water liquid, which is that number, and water vapor, which is this number. We're using water vapor, so it's negative 241.8. Next, I subtract from that the sum of the heat of formation of the reactants. So I go to my reactants. There's methane. 1 mole of methane, so 1 mole. Methane is negative 74.6. Plug that in. And then I add to that oxygen. But you go try to find oxygen on pages 4 and 5. It's not there. That's because elements have a heat of formation of 0. This is an arbitrary assignment, but all elements will be 0. All right. So now we simply do the math. All those moles will cancel, leaving me with kilojoules plus kilojoules. And when I do all of the math, I do this bracket, subtract this bracket, I get negative 802.5 kilojoules. It asked for molar, and molar for methane, there's already one there, so it's the same answer. Negative 802.5 kilojoules per mole. Great. Let's take a look. Oh, and we can put this on a potential energy diagram now. So this bracket's math came out to 877.1. This bracket's math came out to 74.6. So on a potential energy diagram, it would look like this. We're releasing 82.5 when this reaction happens. And I now know that this is my product bracket, the products, and that bracket totals 877.1. That goes down here because these are products here. So 877.1 goes there. These are my reactants. They go here. So that's my reactant bracket. And now you have what a potential energy diagram looks like. We've got an exothermic reaction, and it's properly labeled in terms of energy. Okay, good. Now, you might say to yourself, I don't get why we use heat of formations in this, because this is a combustion equation. Well, this is actually very cool. This is deep. Listen to this. We don't truly just start with these things. They came from somewhere. Now, did they get created spontaneously in nature? Did a divine being create all these things? Well, it doesn't matter to me what you believe about that. But the point is, these were created at some point in Earth's history. Okay? So we don't really start with these yet. Okay? Somehow matter was just all over the place, and then our Earth was formed, and plants grew, and animals grew, and evolved, and all that stuff, right? Okay, so watch. Let's say early in Earth's history, these form. Boom. When those form, something happens. When methane forms, it gives off 74.6 kilojoules. Now, elements, we've never destroyed an element, we've never created an element. Elements, matter cannot be created nor destroyed. And so, we don't know how much energy is in there, so we're just going to assign that a value of 0. Elements are 0. But we can create compounds, and so we can measure that energy. So scientifically, we know 74.6 kilojoules comes out when carbons and hydrogens combine. Okay? These ones we just arbitrarily say 0. All right. Now we come along and we take this methane, this natural gas, out of the earth that has been provided for us, and we burn that methane. Okay, so you turn on your furnace and you burn natural gas in it. All right. When that happens, first of all, we have to start the natural gas on fire. We have to pump energy in. When we break bonds, energy is absorbed. So those bonds are snapped. In order to break methane, I have to pump 74.6 kilojoules in, and it snaps. Okay? Elements, we'll just say 0. Now, those snap. Everything goes into chaos. They get rearranged. And look at, they get formed. Heat of formation. All right, so they just got formed. CO2 just was formed. Water was formed. That's why we used formations in our combustion equation. All right, so the CO2 was formed, the H2O was formed, and when that happened, energy was given off. When bonds form, energy is released. Carbon dioxide gave off 393.5. Water gave off 241.8. Each one of them. So, now you can actually see how this math works. We start with our products. 393.5, one of them. Reactants, 241.8, two of them. Altogether, 877.1 kilojoules was given off when CO2 and water were formed. Now, somewhere in the history of the world when methane was formed, 74.6 kilojoules was released. We come along and we add 74.6 kilojoules to the methane to break it, and that's where we get our negative subtracted negative is positive. So there's our positive value. So everything is included in this equation. To me, that's really cool that we can have an equation that accounts for what we do with this molecule as well as how that molecule came into existence. That is so cool. Anyway, 802.5 kilojoules was ultimately released when we burn methane.